So today we are going to discuss about uh, some numerical problem on laser. But before going to that part, I would like to give you what is the relation of Einstein's A and B coefficient. Einstein's A and B coefficients. A, B coefficients of Einstein. Okay. Now, if we see uh, the three transitions, let us discuss the three transitions. This is state 1, this is state 2, state 1, state 2, state 1, state 2. Okay, first let us consider the induced absorption. Let us consider this is atom and we are giving some energy to that atom, and this atom will be absorbing that energy and it will be raising to state 2. So that is induced absorption, for which Einstein given it a coefficient that is B12. Okay. Then another transition is that that will be downward transition, which occurs spontaneously. Okay. And this transition is supported by another coefficient A21. Since it is coming from 2 to 1, so Einstein's coefficient is A21. Third transition is also from 2 to 1, but it is not happening without any external force or external energy that we are providing. Okay, so since this is also supported by this external source of energy, so it is termed as B21. So there are three coefficients given by Einstein's A and B coefficients, and they have a very beautiful relation, and we are going to see what is the relation they follow. Okay, so the relation between Einstein's A and B coefficients is A21 by B21 is equals to 8 pi h nu cube divided by c cube. Okay, where this h is Planck's constant, and this is nu. Nu is the frequency, c is the speed of light. Okay, so this is the expression of Einstein's A and B coefficient. Then another important point that to be discussed is Boltzmann's relation. Which is given by N2 by N1. Now, what is this to N2 by N1? Let us consider these are the two states, 1 and 2, and let us consider this is the number of atoms in state 1, that is N1. So N1 is the total number of atoms present in state 1, and N2 is the total number of atoms therein in state 2. So the N1 and N2 are nothing but the population. So that is why it is also called as population ratio. So N1 and N2 will be equals to exponential minus E2 minus E1 divided by KT. Okay. Now, what is this E2? Okay. Now, let's see what is E2 and E1. E1 is the energy of state 1, that is given as NH nu, that is here N is 1, so this is 1 H nu, or it is nothing but H nu. Okay. Similarly, E2 is NH nu means 2 H nu. So what will be E2 minus E1? E2 minus E1 then will be equals to 2 H nu by 2 H nu minus H nu, that is nothing but H nu. So in place of in this equation, this E2 minus E1 can be replaced by H nu. So we have the relation that is N2 by N1, that is equals to exponential minus H nu divided by KT. So this is the relation which will be Boltzmann's relation, which we'll be using in our problem. So first problem, let us discuss our first problem. First problem states that, question number 1, okay, it says that a ruby laser is emitting photons. There is a ruby laser, okay, which is emitting photons of wavelength lambda is equals to 6493 angstrom. Okay, and temperature of operation is T is equals to 27 degrees centigrade. Means the temperature in operation is 27 degrees centigrade, where a ruby laser is operating, which is at the wavelength 6493 angstrom. Now, question is to find the ratio of population of the two energy state responsible for the release of photons. Ratio of means what is N2 by N1 is how much? Okay, that is the question. This is a ruby laser. Okay, so let's discuss then. So we have given few informations. We are already having the wavelength 6493 angstrom and temperature which is at 27 degrees centigrade. We have to keep this is in Kelvin temperature, as we know that 0 degrees centigrade means, sorry, we know that 0 degrees centigrade means 273 Kelvin. So 27 degrees centigrade means 273 plus 27, that is equal to 300 degree Kelvin. Okay, so temperature is found. Temperature is 300 degree Kelvin. Wavelength is already given. Our equation N2 by N1 is nothing but exponential minus H nu by KT. So we need to know what is H and what is nu. Okay, as it is given nu is nothing but C by lambda, where C is the speed of light and lambda is the wavelength. So we can rewrite this equation as exponential minus H C divided by lambda KT. So if we put all these values here, then it will be this problem can be solved. So n2 by n1 is equals to exponential minus h. Oh, here h is nothing but the Planck's constant, which is 6.63 into 10 to the power minus 34 joule second. Okay, so that will be required. So exponential h means 6.63 into 10 to the power minus 34 joule second multiplied with c. C means 3 into 10 to the power 8 meter per second, and divided by lambda. Lambda is given 6493 angstrom. Angstrom means 10 to the power minus 10 meter into k. K is Boltzmann constant, that is given as 1.38 into 10 to the power minus 23. And temperature is 300 Kelvin. So if we all solve this all the terms here, then it comes around e to the power minus 73.02. Okay. So for that, we can find, if we take the exponential value of minus 73.02, that comes around 7.35 into 10 to the power minus 33. Okay, so this is the value of this ratio n2 by n1, which is asked. Okay, so this is the answer. 7.35 into 10 to the power minus 33. Now coming to the next problem. Let's take a new page. Add page. Okay. Now, second question is that calculate the wavelength of light emitted at 330 Kelvin. Temperature is given, that is 330 degree Kelvin. Okay. If the ratio of the population of two energy, now n2 by n1 is given, ratio of the population of two energy level is 1.059 into 10 to the power minus 30, out of which one corresponds to the metastable state. So there are two states, state 1, state 2, out of which one is metastable state. So n2 and n1 is given, temperature is given, and we need to find what is the wavelength. Wavelength is not given. So from the same expression, we can find what is the wavelength. Okay. Now how we can solve it? You can solve it by taking the same relation, Boltzmann constant, and 2 Boltzmann relation, and 2 by n1 is exponential minus h nu by kt. Okay, so that is equals to exponential minus h c by lambda kt. Okay, so that is equals to So all these values are given. We have n2 by n1, that is how much it is given. 1.059 into 10 to the power 30. So this value is already given. So we are writing it 1.059 into 10 to the power minus 30, which is equals to exponential minus h. H means 6.63 into 10 to the power minus 34 into 3 into 10 to the power 8 meter per second divided by lambda, not known, lambda to be found out. K is Boltzmann constant, that is 1.38 into 10 to the power minus 23